Welcome to Civil Service IAS, your go-to YouTube channel for all things related to the Indian Administrative Service.
From the tallest sequoia, to the smartest human, to the most poisonous mushroom, to the tiniest bacterium, there is one thing that unites all living things on Earth. And that is the fact that all life is based on carbon chemistry. This element is so important, in fact, that it has its own branch of chemistry, organic chemistry. But carbon is not the most abundant element on Earth. That would be oxygen. And it is not the most stable, like helium. On the surface, it doesn't appear particularly special. Yet, if we look at our body composition, we find that carbon is everywhere in our cells. 20% of our body is made up of carbon, but it comprises less than 1% of the mass of the Earth's atmosphere, oceans, and crust. Why did life go to the trouble of concentrating carbon 20-fold in our bodies, when other more abundant elements like oxygen and silicon were available, or even nitrogen, which makes up 78% of our atmosphere? The big question is why? We're going to examine that, and we're going to trace the logic that nature used in choosing this all-important element, carbon. That's coming up right now. There are 94 naturally occurring elements on the periodic table. Why is everything based on carbon and not something else when the choices are so many? The answer boils down to three things: complexity, abundance, and stability. What do I mean by this? Let's start with complexity. Carbon is able to form the complex molecular structures needed for the complex chemistry that life requires. Why is carbon able to do this? To understand this, we have to look at the foundation of chemistry, which is physics, particularly quantum mechanics. Quantum mechanics tells us that some electron orbital configurations are more energetically favorable than others, making them more stable. And the most stable configuration of electrons are those of the noble gases on the far right side of the periodic table. These are special elements that have a complete outer shell of electrons. This is the lowest energy configuration that an atom can have. This makes them chemically stable because they do not typically need to share, gain, or lose electrons to form bonds with other atoms to become more stable. This is also why they're chemically inert, since they do not generally interact with other atoms to form molecules. Why are only the noble gases this way and not other elements? Because they happen to have the right number of protons to have the right number of electrons to fill their shell fully. The driving force behind chemistry is really a hunt to get to the most energetically efficient state in a system, the state of lowest energy. And for the most part, this lowest energy state occurs when an atom is able to fill its outermost shell fully, like the noble elements. And some atoms can do this by sharing their electrons with other atoms to form what's called covalent chemical bonds. The periodic table of elements is arranged in such a way that we can easily tell by column the maximum number of bonds that an element can form with other elements. Starting from the left column of the table, the first group of atoms can form a maximum of 1 bond. The second column of elements can form 2 bonds. Third column, 3 bonds. This trend continues up to the fourth column, which can form 4 bonds. After this, the maximum number of bonds decreases. So the fifth column of elements can only form 3 maximum bonds. Then 2 bonds, 1 bond, and finally 0 bonds for the rightmost column, which are the noble elements, which are already the most stable. What you'll notice is that carbon is in the group of elements which can form the maximum number of bonds. It has a total of 6 electrons, 4 of which are on its outer shell. In order to fill its outermost shell, it needs 4 more electrons to make 8, like the noble gas neon. So it can share up to 4 additional electrons from other atoms to form covalent bonds, making it more stable. This makes carbon very versatile. Imagine if Lego bricks could be connected on 4 sides instead of 2. It would make building things easier. Each carbon atom can form a strong, stable bond with up to 4 other atoms, including other carbon atoms. This feature of carbon gives it the ability to form complex molecules, which is necessary for the complex chemical functions that life requires. Carbon-based molecules can form long, non-repetitive chains of polymers. They can form closed rings, and they can form single, double, or triple bonds with other elements. There are millions of possible configurations. Taken together, this makes carbon uniquely able to take part in a vast multitude of chemical processes. It can easily form long, stable polymer chains that can, for example, carry a lot of information. This is the case for DNA. DNA, after all, carries all the information that makes up living things, including us. And the 4 nucleotides that make up the building blocks of DNA are complex. Carbon is the backbone, partly because it can handle this complexity. The other elements are not as interesting. Take, for example, oxygen, which is the most abundant element on Earth. It can form only 2 bonds. This means that once it bonds with 2 other atoms, it's done. It can't really form interesting scaffolds of complex molecules, like carbon can. Boron could be interesting because it can form 3 bonds, so its molecular structures could also be fairly complex. The problem is that it's extremely rare, so it's just not very available for life to have chosen it as its backbone. This brings us to the second factor that made carbon attractive for life to latch onto: abundance. Not only is carbon versatile, it's also abundant. If we look at the top 5 most abundant elements in our solar system, what we will see is the following in order of abundance: hydrogen, helium, oxygen, carbon, and nitrogen. Now, if we look at the top 5 elements in our body, what we will see is the following in order of abundance: oxygen, carbon, hydrogen, nitrogen, and calcium. So what we see is that 4 out of the top 5 elements of the solar system are also among the top 5 elements making up the human body. This gives us another clue about why life is based on carbon. There's plenty of it in the universe. It's very abundant. It's easier to build something that you have a lot of. You can't build a castle if you don't have enough Lego bricks. At this point, you might say, if abundance is so important, then what about silicon, which is abundant and can also form 4 bonds? Or nitrogen, which can form only 3 bonds but makes up 78% of our atmosphere? This brings us to the third factor in determining the most suitable element that nature chose for life: stability. What I mean by this is bond stability. Let's look at that. As I said earlier, the structure of the periodic table is such that, as a rule of thumb, all elements in each column have the same general properties. Carbon turns out to be the lightest element in the group of 14, or 4, depending on how you count. Therefore, we would expect that the sister elements, like silicon and germanium, would have similar chemical properties. Silicon is the next lightest element in the column. Its position on the periodic table tells us that, like carbon, it also has 4 valence electrons. This means it can also make 4 covalent bonds. For every molecule made out of carbon, there can be an analogous molecule with silicon in its place. Silicon also happens to be quite abundant on Earth. In fact, there's more silicon on Earth than carbon. It's just locked up in rocks within the Earth's crust. Chemically, silicon has 4 unpaired electrons in its outer orbital, just like carbon. The main difference is that silicon has its unpaired electrons farther away from its nucleus, on its 3rd shell, whereas carbon's electrons are on its 2nd shell, closer to the nucleus. This makes silicon's electrons more weakly bound to its nucleus. The consequence of this is that when silicon bonds with other atoms, including itself, the bonds formed are weaker and thus less stable. To give you some numbers, the silicon-silicon bond strength is 196. In contrast, carbon-carbon bonds are stronger at 334. This bond strength factor is also a reason nitrogen is not well suited to be the backbone of organic chemistry, as its bond strength is roughly half of carbon. You can't make a skyscraper with a foundation built from cardboard. The structural support has to be strong to hold the walls, windows, and doors. Organic molecules have the same need. The backbone has to be strong enough to withstand the conditions under which other parts of the molecule break their bonds and react chemically with other molecules. So the carbon-carbon scaffold needs to remain intact while the functional components break apart. A molecular scaffold made from nitrogen or silicon would more easily break apart. So if we go back now to the periodic table and look at the 3 rows of elements, if we remove all the chemically inert elements and then remove elements that can't form more than 2 bonds, then we remove all the elements that are exceedingly low in abundance, we end up with carbon, nitrogen, and silicon. Then, if we remove those that cannot form strong single bonds to themselves to create a strong molecular backbone, this leaves pretty much only carbon as the best choice. It is uniquely suited for life because of the best combination of abundance, ability to form complex structures, and logic. We can also imagine life based on germanium, tin, or even superdense creatures made of lead. But we have to keep in mind that as elements get heavier, they tend to be more rare. So each of these is less plausible than the last. For example, germanium is at least 5 orders of magnitude less abundant than carbon, and tin is even rarer. It so happens that the pressures and temperatures on Earth work well for life forms that use liquid water as the solvent, and carbon-based molecules that can form a stable backbone on which biological chemistry can take place. If it gets too cold, water turns to ice and we'll have problems with chemical transport. If it gets too hot, we'll get issues with carbon polymer chains breaking too easily. We may never know for sure, but it's perfectly possible that carbon trumps everything else except in extreme environments. But we can't rule anything out, and we need to be open-minded about conditions in which life could hypothetically occur. For example, there are lakes of ethane and methane on Titan. Under the conditions of Titan, these are liquids. And like water on Earth, they could be used as a solvent by a different type of life form. So at different temperatures and pressures, it is conceivable that a different element may be more conducive to life. One of my Patreon supporters pointed out that we carbon life forms may right now be in the process of creating silicon artificial life forms. And this process is accelerating. This form of life could very likely exist in the near future right here on Earth. But there's no evidence for life outside of Earth. It could be quite rare in the universe. So you can have all the various elements available in abundance, but the interactions or chemistry of these various elements is the critical process needed for life to happen.